A short introduction again, because this video is to be understood more as a follow-up to this linked video. This video series, within the framework of nuclear waste disposal research for high-level radioactive waste material, addresses the question, what do radionuclides do in the environment? Since a deep geological repository is the safest method to store high-level radioactive waste within a multi-barrier system, a natural question arises: high-level radioactive waste and rocks, can they interact? Yes. And one type of interaction that is particularly interesting for us is the immobilization of radionuclides. Radionuclides can move through passive processes uncontrolled. Logically, it makes sense that we want to prevent radioactive substances from wandering around freely. So immobilizing radionuclides is key. This can also be achieved with the help of minerals. In the first video, we looked at the immobilization of technetium by the iron 2 containing mineral pyrite. It turned out that pyrite can very effectively immobilize technetium present as pertechnetate through redox processes, reducing technetium from the oxidation state of +7 to +4 and absorbing it via various pathways. Of course, not every mineral can precipitate in redox reaction. Some elements are stable only in one oxidation state, for example aluminium. Aluminates, or aluminium compounds containing aluminium 3+, which under these conditions cannot really gain or lose any electrons. It's not redox active. Nevertheless, other non-redox active minerals help immobilizing, for instance, also technetium. But why is mobile technetium a problem? When I refer to technetium, I mean technetium-99 in its ground state. This is a low-energy beta-minus emitter with a half-life of about 210,000 years. Technetium-99 can enter the environment as a fission product through various human activities. One pathway is via the excretion of medical injected technetium-99m used for diagnostic purposes. Technetium-99m has a very short half-life and will convert into the technetium-99g at the latest in the sewage system. There are guideline values for radionuclide content in drinking water. Annual radiation exposure for beta-gamma radiation via drinking water must not exceed 40 microsieverts. Our case example, technetium-99g, is such a beta-minus emitter, and it had been shown that marine organisms like crabs and lobsters can accumulate technetium after contact with contaminated water from the British reprocessing facility Sellafield. Technetium contamination is thus a real problem. Technetium is relatively new as an element, and there is limited chemical data available on this intriguing element. Today we will take a look at applied research on exactly this issue: the immobilization of technetium by non-redox active minerals. Minerals that do not contain elements capable of redox reactions. One analytical method is the ATR-FT-IR, Fourier transform infrared spectroscopy, which I will briefly explain now. This technique uses a Fourier transformation to process the data. ATR-FT-IR can provide information about radionuclide absorption on mineral surfaces. It can also indicate the chemical form in which the radionuclide is present. So now some basics about infrared spectroscopy, aka IR spectroscopy. Chemical bonds can vibrate in various ways. Atoms in a bond are not stationary at room temperature. If a vibration changes the dipole moment, the charge distribution in a molecule, it becomes IR active, meaning it can absorb infrared radiation. Each vibration absorbs different wavelengths, allowing us to assign absorption bands to specific bonds and piece together the molecule. When a radionuclide interacts with a mineral surface, it can form different types of adsorption complexes. Outer sphere absorption with the hydration shell still on it, inner sphere absorption with a direct interaction with the mineral atom, and some more. These interactions cause measurable changes in the mineral's IR spectrum. Now onto the experimental setup. An IR beam passes through the ATR crystal, which is diamond in this case. The mineral sample is on top of it. The IR can penetrate through the thin mineral layer into the solution above the mineral, and when radionuclides are introduced, interaction can be measured. Afterwards, the radionuclides can then be rinsed off to study the desorption. Mineral suspension, usually between 2 and 10 microliters, are pipetted on the 4x4mm diamond crystal and then dried. Too much material leads to total absorption, preventing the IR beam from reaching the solution. This apparatus delivers the radionuclide, a blank solution, and possibly a ligand. The blank needs to match the original radionuclide solution in composition, electrolytes, and pH value, for example. The system can then automatically switch between blank, ligand, and radionuclides, letting the solution flow over the mineral in a desired sequence. If working Cooking with a radionuclide like Neptunium, the solution doesn't drip out into a glass beaker like here, but will be contained in a closed system. I think it's a very elegant system that you can just put in the bulk solution and the program can do the rest of the experimenting. This setup contains an interferometer with 2 mirrors. When both mirrors are at the same distance from the beam splitter, constructive interference gives a strong signal. The measured signal, intensity versus mirror position, is then converted by a Fourier transformation to a frequency-dependent absorption, revealing bond-specific information. Dr. Natalia Mayordomo and colleagues published a study on absorption capacity of gamma alumina particles for pertechnetate. Alone, gamma alumina is not very effective at immobilizing pertechnetate, but adding iron 2+ dramatically increased retention. The material was artificially prepared, so an iron 2 chloride solution was added to aluminium chloride, and at a pH of 4.5 it produced a layered doubled hydroxide, LDH for short, of alternating iron and aluminium hydroxides. The chloride ions can reside between the layers. When pertechnetate is introduced, an ion exchange can trap some of the pertechnetate ions in the LDH layers. And this was measured with ATR-FT-IR. So this analytical tool is very precise. A blank measurement and a sample measurements are taken, and the difference in the order of 10 to the power of -4 indicates that pertechnetate has exchanged some of the chloride ions in the LDH layer. This method can also provide many more insights, like uranium complexation by peptides or neptunium absorption on hematite. And now we know a bit more about this analytical tool. Thanks to Dr. Harald Foerstendorf and Carsten Heim, who did all of the lab work for today's video. And to Dr. Natalia Mayordomo and Dr. Katrin Müller for organizing this video. Also a big thank you goes out to Professor Dr. Stumpf as Institute Director and to my Patreons for their financial support. With that being said, thank you for your attention and goodbye.